So today's topic is an introduction to nonlinear dynamics in Abaqus. We'll see today what's the difference between linear and nonlinear, and why do we actually consider dynamics at all. So to begin with, just a few short words about Intrinsys. We are an engineering consultancy firm established in 1998. Who among the consultancy business, we are also a PLM consultancy. We are UK's largest VAR for Dassault Systems products. Our business employs 64 people in the PLM side and 85 on the engineering consultancy side, and we have 4 offices in the UK and 1 in South Africa. So just a few words about the PLM Solutions. So we are a Dassault system reseller. We sell the 3D Experience platform licenses, also CATIA, Anovia, Delmi and Simulia, so the complete Dassault system portfolio. In addition to software sales, we provide support, training and consultancy using the software. The other side of the business, the engineering services, we also offer design consultancy, so we can take the product from concept all the way through the detailed design stage, help you with material and process selections, prototype supply and component testing. We are, in addition of supplying simulation products, we are expert users, so we deal with linear, nonlinear, thermal, dynamic and other different types of analysis. We have years of expertise in press tool design, styling and so on. So this was just a few quick words about Intrinsys, and then let's see what are we going to discuss today. So first of all, we're going to look at what simulation procedures we have in Abaqus, where and how does dynamic simulation tie into that. Then we look at linear and nonlinear dynamics. We see what's the difference between an implicit and an explicit dynamics. And at the end, we are going to look at some examples of what sort of nonlinear analysis you can do using Abaqus. So to begin with, simulation procedures. Now what everybody who has ever done a simulation is familiar about is the static stress. So this is where you have to constrain your model and load it, and then you will see what is the static deformed shape. This is the classic and also the simplest FE simulation you can have. However, there are problems which are more difficult or different in nature, so you cannot simulate it using the static procedure. For example, buckling, which is very important for slender and long structures. Also direct cycling, which is very important if you have regions of yield, small regions of yield in your structure. It is important to run the cyclic analysis to see what is the effect of these yields. Are they going to stabilize, or are you potentially introducing fatigue issue into your part? Then dynamic analysis will be the topic of today's webinar, so we'll go into this in more detail. Heat transfer is slightly different than the previous ones, so instead of solving for structural deformations and stresses, we're going to solve for temperatures and heat fluxes within the part. So heat transfer does not take any deformation into account. Now in Abaqus you have various options to combine the heat transfer simulation with a structure simulation, in which case you can get the combined effects of temperature and structural deformation. CFD is the fluid dynamics part of Abaqus. CFD, instead of solving the structure itself, it solves for the flow field around the structure. The most common fluids are air or water that are in engineering use. So CFD allows you to solve for pressures, temperatures, and velocities within your flow field. Steady state transport is a very useful tool if you want to analyze, for example, rolling tires. It allows you to very efficiently and cost effectively analyze large rotating assemblies, for example. Electromagnetics is also part of Abaqus. It lets you solve for electric and magnetic fluxes in your part. Again, you can combine that with structural models and work out heat generated, for example, or deformations due to the electromagnetics. But for today, our main topic is going to be the dynamic analysis. So we can ask the questions, when are dynamics effects important, or rather, the main question is, when can we ignore them? Because if we can ignore dynamic effects, then we can make our lives easier and use a static analysis, for example. However, there are many cases where they can't be ignored, such as when you have high kinetic energy and impacts. So these are all the crash and impact type analysis. You have, for example, time-dependent behavior, for example, strain rate dependent materials. Then you must simulate your structure in the time domain. You can have snap-through or collapse type behavior, which again, you might be able to simulate it with a static procedure, but a dynamic procedure definitely handles it. Also, if you have very large displacements, large rotations, or other mechanism in your model, then dynamic simulation is probably the way to go forward. In terms of what problem types we are going to look at, we have fundamentally two. So we can have a truly dynamic, in which case all these high kinetic energy and large displacement, these are very important. Or we can have a quasi-static type analysis, in which case we are using the dynamic procedure to make sure that we are solving the problem. So it helps you to overcome some of the limitations of a static solver. For example, parts don't have to be constrained in a dynamic analysis, as opposed to the static, which we all know, if we don't constrain the parts, we're going to end up with zero determinant, and then we are not going to solve our problems. So linear dynamics, we had an excellent webinar on this a few weeks ago. Just a quick recap. So linear dynamics is small linear displacements around the base state, and relatively few frequencies dominate the response of the structures. So we can work out those few modes, for example, and then predict the response by using only those few modes. As there's mainly two types, so you can have a free dynamic. So this is the general, sorry, this is generated by internal system forces. So this will give you like the free vibrations, or you can have forced vibrations, which is due to your applied external loads. And also either procedure can include some amount of damping, which generally tunes your nature frequencies and reduces response of your structure. So this is all linear dynamics. As you can see, we have a lot of different procedures that we can run in Abaqus. So every linear dynamics procedure will require almost a frequency extraction, which would generate your mode shapes. This can be real or complex. Then you can run a transient response, which is simulated in time domain. You can run a steady state response, which is simulated in the frequency domain. So this would be a frequency sweep. So let's say from 100 hertz all the way to 10,000, 100,000, as high as you want to go. Response spectrum would give a response from your part when you apply load spectrum, using spectral density. Similar random response would give you your structure's response to a random loading, which you have to describe in a statistical sense. And most of these procedures, you have different options. You can either use a model decomposition or a direct simulation or a subspace-based. Basically, to summarize very quickly, a direct is usually the most expensive in terms of computation, but it's usually the most accurate. Model is the least expensive, but it assumes that your model shapes stay constant, and subspace is somewhere between the two in terms of computation and accuracy. So these are all the linear dynamics, which should be familiar by now. And now we take a look at the nonlinear dynamics. So in the nonlinear dynamics, you have three main procedures. You can have implicit dynamics, explicit dynamics, or subspace-based dynamics. Now in the following slides, we're just going to go through each of these and see what's the difference. So to begin with, linear dynamics, as we see, is always around the base state. So we linearize the response of the structure, and we are going to approximate the behavior with this linearized curve, while for a nonlinear dynamics, we actually solve all the equations of motion, and we produce a true dynamic behavior for the structure. So in the nonlinear dynamics and implicit dynamics, it means it's implicit time integration. In this case, it's the general response of the structure what we are interested in, not the propagation of every wave in the structure. This is an accurate method, as it's unconditionally stable, and it can take relatively large time steps, which are fairly long. It takes fairly long to solve. It can be geometrically linear or nonlinear, and you can include various levels of numerical damping in your solution. So if you are interested in all the high frequency modes, you have to use a transient fidelity because that has the least amount of damping. If you are just interested in the general behavior of the part, for example, if you are doing a forging simulation or something similar, you can use a quasi-static, which has high numerical damping, so it would damp out most of your high frequency response, and you will only end up with the general low frequency response of your structure. So where would we use it? Typical application could be a powertrain analysis, and or other mechanical type of analysis where you have mechanism in your part. Okay, so that is implicit dynamics. Now the next topic is what's the difference between explicit and implicit dynamics. Basically, the main difference is this integration scheme, and the explicit time integration means that you always work out your next increment from the previous one explicitly, so just using a small time increment and the accelerations and velocities. This procedure can capture all the wave propagation in the structure. However, it's only conditionally stable. That means it must take small time increments. We'll take a look at this one in more detail. And although it has to take a lot of small time increments, one increment is much more cost effective than an implicit analysis. So as you see on this graph, an implicit analysis for low number of degrees of freedom is usually a better choice for dynamic analysis, but after a number of DOFs, the explicit analysis is usually a better choice because the time it takes increases pretty much linearly with the number of elements, while the implicit is a power law. So for very large problems, explicit is usually the choice. So in terms of typical applications, we'd use explicit analysis for impact or crash type analysis, blast, extreme deformation or forming, and also we can use it to model fluid behavior. Now, subspace dynamics is uses a method called the modal subspace projection. What this means is we work out the mode shapes of the structure, and we're going to use those mode shapes to run a nonlinear analysis using an explicit integration. So where is this good? This is very good if we have nonlinear behavior for the whole model, but the actual components have only mild nonlinearities, so the mode shapes pretty much stay constant during the analysis. And what's the big benefit of this is our stability limit is going to set by the highest eigenfrequency instead of the actual structure's stability limit. That means these type of analysis can run much faster than an explicit analysis because you can take much higher time steps. Drawback is you cannot use it for contact type problems. And for example, a typical application is like a full vehicle dynamic analysis, in which case each individual part of the vehicle, so each individual part behaves linearly, but the vehicle as a whole can have nonlinear behavior. Okay, so these are different procedures. Now we can see what sort of modeling practices we need to use for these simulations to work well. So in terms of modeling, first of all, we need to have an elastic behavior for at least an elastic behavior for every element, and we also need a density specified. So for static analysis, we'd only need elastic behavior. Now we add the density because of the dynamics. We also have to use accurate initial conditions if we are running a time accurate analysis. For example, if we don't set initial speeds or accelerations right, then we can end up with like a large discontinuity at the beginning of the model, which could cause very high stresses and that would definitely give us wrong results. Also, we need to provide realistic amplitudes. For example, if you look at these images to the right, what we use for static analysis is a classic amplitude curve. In the case of a static analysis, it doesn't matter how we change it because we are only working out the final solution irrespective of how we got there. However, in the case of a dynamic solution, if we do this, as we can see, if there's a kink in the displacement, that means that there is a step change in the speed, because the speed is a derivative of the displacement. And if there's a step change in the speed, that means we have, well, either infinite or at least very high accelerations. And all these very high accelerations would generate shock waves into your part, which is not good because these are not present in reality. These are only present because you defined a kinked displacement curve. So how to get around this? You can use the smooth amplitude, smooth step amplitude in Abaqus, in which case you will still define these points, but Abaqus will automatically smooth your response, in which case, as you see, there's no more step change in your speed, but there's a gradual change, and thus you end up with a finite acceleration. So you wouldn't have those issues as in this case. Now, obviously, this is an approximation automatically done by the code. So if your structure is very sensitive to what's happening here, then you must refine your amplitude curve here, and you actually have to put your actual loading that you want to see. But that is only applicable if your structure is very sensitive to this. Most of the times, this is not an issue. Okay, so we mentioned this stable time increment in Explicit. What's this? This is basically a limitation on how large your time step can be, and this is limited by the time it takes for the wave, for any wave in the structure to travel through your element. So obviously, the smaller your element, so L is your element size, then this time increment is smaller. Likewise, if you have a stiffer element, so for example steel is very stiff, then because we are dividing by the stiffness, it will have a very low time increment limit. However, the more dense your part is, because we are dividing by 1 over density, that means the higher the density, the higher we can get our limit. So in this table you can see typical examples. So steel, usually it's about 200 GPa, Young's modulus, and about 7,800 kilograms per cubic meter. So that would work out to have about 5,000 meter per sec wave speed, and that results if we assume that you meshed with a 1 millimeter size element, which is not too small. You can easily have much more refined meshes. Then your critical time increment is 1.97 e to the minus 7, which would mean if you want to simulate an event that lasts for 1 second, you would need to do 5.1 million increments. Now that's a lot of increments, especially if you have very large models. So it's always a good idea to design your mesh to keep in mind how are you going to get this time increment as high as you can. Because if you see this very simple example, you can have nice large uniform meshes, not large parts, but if you have a few tiny elements, because the whole procedure is limited by the smallest time increment, even one of these can potentially reduce your time increments potentially to E-9, E-10, even lower, in which case it can take about 1,000 times more time. So if with E-7 increment you might finish your simulation in 1 hour. If you don't design your mesh well, it might take you 1,000 hours to run it, which is clearly something you don't want to have, because you will never be able to solve your problem. So how can we get this high, or how can we ensure that this delta T stays high? We can first of all look at the problem, and we have to know, are we actually running it for a full second? Because lots of the dynamic, for example, blast or crash type of problems, they don't last a second. They might be 100 milliseconds or 10 milliseconds. So make sure you understand what is the simulation time that you're going to run. Also, try to use undistorted and large elements, which would mean you get a high L value in your equation, which increases your stable time increment. Time scaling, you can run your simulation actually faster. That means, for example, if your forming process lasts for a second, you might be able to simulate it in 100 milliseconds or 10 milliseconds, provided you're not changing the result. We'll see a few slides in a minute where we discuss this, that what is the limitation on this. Similarly to the mass scaling, if you remember the equation, as we discussed, density, increasing density would increase your time, the allowable time increment. If you scale up the mass, so scale up the density of your elements, that effectively raises your wave speed. So that means you can take higher time increments for the same mesh size. Now, it's very important to be aware that both time and mesh scaling is not appropriate if you're running a real-time true dynamic analysis, which is, for example, a crash or a blast type analysis. Where it can be used is for quasi-static analysis. So these are usually, for example, forging or sheet metal forming type of analysis. And you have to make sure that it doesn't affect the results. Also, where you can use it is if you have only a few little elements, maybe a few isolated little elements that would spoil the critical time for the whole analysis, then you can choose to just selectively scale those elements, in which case, again, once you get your result, you would have to double check that you haven't introduced anything into your simulation that would change your result. So how can you check that? First of all, you have to check your energy balance. It's a fairly long equation, but what this means is in your simulation, your total energy throughout the simulation has to be constant. Now, due to round-off errors and all that, it's usually within 1% of its actual value throughout the simulation, but generally it shouldn't change. So that means whatever energies you put in, they can only convert from one to the other. So to simplify it, what you always have is work done by your external loads, and that work, in the simplest case, would go into an internal energy and into kinetic energy. Now, in a case of a quasi-static analysis, what you want to ensure is your kinetic energy is small compared to your internal energy, which is made up of the elastic strain energy and the inelastic dissipated energy, which is, for most of the metal basic type applications, this is the plastic deformation energy. So that means all the work you put in should go into elastic strain energy and plastic deformation and very little kinetic energy. If this is true, then you're running a quasi-static analysis. So how can we see this? This is an example of an analysis what I run, forming of a steel or an aluminium bar. As we can see, if we run it in real time, obviously this takes the longest to run. Then the work we input is equal to the strain energy, but our kinetic energy is pretty much zero. So we might see a little increase in kinetic energy, but for all intents and purposes, this is negligible to the work. Now, if we increase the simulation time by 10, what we can see is we start to have more kinetic energy because everything is happening faster. This time I used mass scaling actually to increase the time increment. So because there's a square root in the equation, 10 times time increment increase translates into 100 times mass increase. But as we see, this increase in kinetic energy is still negligible compared to the work. Now, once we go into 100 times increased, you can see that we start to get huge effects from the kinetic energy, and as we increase the mass scaling more and more, we can see that we're not only increasing the ratio of kinetic energy to the total energy, we're also increasing the total energy that we have. So this is definitely has a very large impact on our analysis and on the accuracy of the analysis. So based on this, if you had to choose, you either have to choose real time, or you can go up to maybe 10 times with mass scaling. This obviously takes 10 times less. Now you can ask the question, why would you want to increase your time increment 100,000 times? But if you think about it, if some of your elements, as we see in a 1 millimeter element, would have a 1e7 time increment. Now if it's skewed and distorted, it might be, even if it can be, let's say, 10 microns wide, then that would increase your that would decrease your time increment, maybe E minus 9, E minus 10. So if you have a very large model and you want to solve it in reasonable time, maybe it is required. 100,000 is probably too excessive, but you have to make sure whatever you set, it must not affect your results. So to give you an even better picture, because the graphs are not that clear to see, this is the simulation in real time, then with the 10 times mass scaling. As we can see, there's a slight difference in this region in the results that we are getting. So we are affecting the result. However, what happens here does not really affect the whole behavior of the structure. But as you can see, as we increase speed to 100 times, we get significantly different results here. With 1000, the behavior is completely different. So instead of a straight bent part with local plastic deformation, now we get two local plastic areas. The more we increase the mass scaling, the more the inertia effects become dominant. So this is obviously a very high mass, and at 100,000 times the results are just completely useless, and this is something you should definitely avoid. So just to see again, so this is a local yield and mainly elastic response. This response is not significantly different, but it takes you 10 times less time to run. Now we start to introduce errors. This is now a completely different result. This is also, it's just not what you want to do or want to simulate, and that is just clearly wrong. So this is probably the best way to describe how to use mass scaling and time scaling. You always have to check your result, and you always have to know what you are running. It's always worth running especially large models with large mass scaling and going the other way, because these take the least amount of time as opposed to running it, because this might take tens of hours while this might only take 6 minutes. So it's always worth to use mass scaling wisely if you can. So let's just go on to some examples of where you can use these. This is a typical crash and impact type analysis. The one below is a fracture. So you can simulate all these using explicit dynamics. This is a mechanism. As you can see, the overall deformation of the structure is nonlinear, but each component is acting in a linear fashion. You can have nonlinear materials, nonlinear behavior, and nonlinear contact. You can also simulate organic structures, which are, again, they all behave in a nonlinear fashion. You can crash. Impact is a typical, or the loss of a turbine blade. This is nonlinear. Buckle and collapse of structures, or just general almost the soil is sort of a fluid type behavior. So again, this is something you can simulate with nonlinear dynamics. Again, another perfect example of crash. So car side crash and airbag inflation. This is a blast type analysis, or drop of a consumer electronic device. And another, what we discussed, is a quasi-static analysis. So here the dynamic effects are not that important, but what's important is we got large deformation and changing contacts. So this is a type of analysis what you would definitely want to use nonlinear dynamics. Again, the general contact capability is a very good feature. It's widely used in Abaqus Explicit. It's worth using it whenever it's possible. So it would allow you to simulate like these stacks of wood or stacks of anything else collapsing without having to set up one by one which part could come into contact with what. Or you can also simulate this advanced behavior, complex behavior of basically putting a tissue into a dispenser. Again, if you wanted to set this up with contact pairs, you might be able to, but general contact is just so much simpler and more effective. Another feature you can use in Explicit is a periodic media transport. So what this would do is it would just make this loop, make this belt of product infinite. So it just keeps going and going in your simulation. You can simulate fluid type behavior. So this is a CEL. So it's a coupled Eulerian Lagrange type analysis, and this is an SPH, which is a smooth particle hydrodynamics. Just very quickly about SPH. So in this case, you model the fluid with little particles, and there's a so-called kernel function which works out the interaction between the particles based on a defined behavior and their distance from each other. So with this you can simulate like sloshing water, again water. This is an impact, so it does not have to be fluid. You can turn steel or other solids into particles, or you can simulate, for example, paint. You can simulate mixing or solid and fluid interaction. These are all possible using explicit dynamics and the SPH. Well, thank you very much for your attention today. I hope you enjoyed the webinar. If there are any questions related to what you heard today, please just ask now, and then we can discuss it. Or if you have any comments or anything else. Okay. In case there are no questions, then I would really like to thank you for attending today's webinar, and hope to see you back on some of our next ones. Thank you very much.